Welcome to the numerical problems that we will solve regarding the vibration absorber theory that we discussed. So, we discussed about the vibration absorber and that this is an dynamic system that when attached to the main system which is vibrating under some excitation force, it can bring the main system to rest. Okay. So, we will have one numerical example. So, here we see that there is a motor generator set and there is some unbalance in the motor, okay, usually there, and they have some vibrations due to those unbalanced forces, and therefore we can attach some vibration absorber here so that the vibration of the main system, that is motor generator set, can be bring to the vibration absorber. So, it is said that the motor generator set is designed to operate in the speed range of 2000 to 4000 rpm. So, its speed range is 2000 to 4000 rpm. However, the set is found to vibrate violently at a speed of 3000 rpm due to a slight unbalance in the rotor. And it is proposed to attach a cantilever mounted lumped mass absorber system to eliminate the problem. So, at 3000 rpm, the system is vibrating violently. It means this is the natural frequency of this system, that is omega 1. And to reduce this vibration, when there is some trial, it is found that 2 kg mass can be tuned to 3000 rpm. So, tuned means it is a tuned absorber. So, tuned absorber omega 1 equal to omega 2 and mass m2 is 2 kg, and it is tuned to 3000 rpm. So, it is 3000 rpm. The resulting natural frequencies of the system are found to be 2500 rpm and 3500 rpm. So, here they are, when we attach this 2 kg tuned mass absorber, the resonant frequencies are found to be 2500 rpm. So, omega 1 equal to 2500 rpm and omega 2 equal to 3500 rpm. Now, we have to design the absorber so that, means we have to find the mass and stiffness so that the natural frequencies of the total system fall outside the operating speed range. So, we have the operating speed range this, but my system is designed for this range and this frequency. So, this is the natural frequency of the system, but we have to shift the range from 2500 to 2000 and 3500 to 4000. So, we can now have, so we have omega 1 equal to omega 2, that is 3000 rpm equal to 3000 into 2 pi by 60. So, we convert into radian per second, and omega 1 equal to 2500 rpm, we convert 2500 into 2 pi by 60, and omega 2 equal to 3500 rpm. So 3500 into 25 by 60. So we can convert them into radian per second. So it is 314.16 radian per second. Now we know that the frequency is omega by omega 2 square, that is equal to 1 plus mu by 2 minus plus under root 1 plus mu by 4 into mu. So this is the resonant frequency, and we can solve this. So let's take first the omega 1 by omega 2. So and we assume it as R1, the ratio of these two frequencies. So R1 square, okay, so it is R1 square, that is equal to 1 plus mu by 2 minus, so we first take the lower frequency, so 1 plus mu by 4 into mu. So we can write R1 square minus 1 equal to mu by 2 minus under root 1 plus mu by 4 into mu. So R1 square minus 1 whole square equal to, so we can do whole square here, so mu by 2 whole square. So if we do whole square, so mu by 2 whole square plus 1 plus mu by 4 into mu minus 2 into mu by 2 under root 1 plus mu by 4 into mu. So here we can write mu square by 4 plus, so we can take mu as common, so we have mu by 4 so because we take one mu outside, so mu by 4 plus 1 plus mu by 4 minus mu and minus so these two cancel out, mu is outside, so we have under root 1 plus mu by 4 into mu. So we can have mu by 4 and mu by 4, it is mu by 2. So mu into 1 plus mu by 2 minus under root 1 plus mu by 4 into mu. And this term is nothing but r1 square. So we can write mu into r1 square. Because here we have r1 square for the lower frequency we are working. So 1 plus mu by 2 minus under root 1 plus mu by 4 into mu. So we see that if we solve this, we find that mu into r1. So now we have separated mu from this expression. So we put in terms of r1 because we know the r1. R1 is omega 1 by omega 2, and omega 1 here we have this value 2500 rpm, and omega 2 is 3000 rpm, and we can find the mu. So we finally find this r1 square minus 1 whole square. So r1 square minus 1, so we can write mu equal to r1 square minus 1 whole square by r1 square. So we now calculate the mass ratio mu for this system. So mass ratio we can calculate So what is R1? First we calculate R1. So R1 equal to omega 1 by omega 2, and omega 1 is 261.75 and omega 2 is 3000 rpm, that is 314.16, and so if we calculate, it is 261.75 divided by 314.16, and we get it is 0.833. So we get R1. Now we put here, we will get mu. So 0.833 square minus 1 whole square by 0.833 square. So it is 0.135. So this is the mass ratio, that is 13.5%. So the mass of the absorber is 13.5% of the mass of the main system. So what is the, so it is M2 by M1 equal to 0.135. So M1 equal to M2 by 0.135. And what is M2? M2 is 2 kg So we put 2 by 0.135. So it is 14.81 kg. So the mass of the main system, that is motor generator set, that is 14.81 kg. Now we have to shift this omega 1 to 2000 rpm. So we want to know what will be the mu in this case. So for R1 equal to omega 1 by omega 2. So omega 1 is 2000 and omega 2 is 3000 rpm. So we have, this is 0.667, this R1. Now if we put R1, we can know what is the mu that is required. So mu is 0.667 square minus 1 whole square by 0.667 square so this is 0.6926. So means now we need 69% of the mass of the vibration absorber. So for this value of mu, what will be the omega 2? So if we use this mass ratio, what will be the omega 2? And so we can find omega 2. So omega 2 omega 2 by omega 2 square equal to 1 plus mu by 2 plus under root 1 plus mu by 4 into mu. So we take plus sign for the higher frequency. So omega 2, so we put 1 plus mu is 0.6926 by 2 plus under root 1 plus 0.6926 by 4 into 0.6926. So we can solve it. So that is 2.248. So we can find omega 2 equal to omega 2 by omega 2 equal to under root of this quantity. So it is 1.5. And so therefore we find omega 2 equal to 1.5 into omega 2, and omega 2 is 3000. So that is 4500 rpm. So the the higher resonant frequency is coming to 4500 rpm. So we are already away far from the required range 4000 rpm. So this is a satisfactory acceptable solution. So finally my absorbers, we select mu equal to 0.6926. So we decide mu equal to 0.6926 and m2 by m1 equal to 0.6926, and m1 we have already calculated. So m1 we already calculated, and that was m1 was 14.81 something. So m2 equal to so it is 10.26 kc. Now K2 equal to m2 into omega 2 square. So we have (10.26) into, so omega 2 was 3000 rpm and it was 314.16 square. So we find that it is 1.01 into 10.6 Newton per meter. So we saw that for the given problem we have selected an tuned mass damper, tuned absorber, that is keeping the frequency range that is out of the beyond 2000 to 4000 rpm. And we find the m2 and k2, that is the design parameters of the vibration absorber. So now we have another problem. So there is a diesel engine that is supported on a mount, and this engine is, the operating speed is 6000 rpm. Now we have to determine the parameters of the vibration absorber that will reduce the vibration when mounted on the pedestal. The magnitude of the exciting force is 250 Newton and the amplitude of motion of the auxiliary mass is to be limited to 2 millimeter. So we have a diesel engine that is weight is 3000 Newton, okay, and our operating speed is 6000 rpm. So if we say determine the vibration absorber parameters, so we have to find the m2 and k2, the mass and stiffness of this parameter. So here we can have this problem we can solve. So we know that here the F0 equal to minus K2 into X2. So and so we can, because here the force is 250 Newton, the amplitude of the force, that is 250 Newton, and if we just take the magnitude, so we will have K2 into X2. X2 is the motion of the amplitude of the auxiliary mass, that is the mass of the vibration absorber. So 2 mm, so it is 2 into 10 power minus 3 meter. So we can find from here K2 is 250 by 2 into 10 power minus 3, and we find it. So this is 1.25 into 10 power 5 Newton per meter. So this is the stiffness parameter. Now we have to find the mass, and to find the mass, as we know that we have omega 2 equal to root K2 by m2. So it means that omega 2 square equal to K2 by m2. So we can find m2 equal to K2 by omega 2 square. Now omega 2 is the frequency, that is the operating speed, 6000 rpm. So omega 2 equal to 6000 into 2 pi by 60. So that is 628.32. So we have K2, that is 1.25 into 10 power 5, and omega 2 628.32 square. So that is 0.3167 kg. So the mass of the absorber is 0.32 kg kilogram. And so we find the design parameter of the vibration absorber. Okay, so I stop here, and I thank you for attending the lecture. See you in the next lecture.